So basically all that code is pretty much visible. If you go into the directory, you'll find here the Windows 10 Systems Programming PDF, and that has all the necessary information that you need to understand the code and to also better develop the code by walking you through the necessary APIs to ensure that everything is pretty much understandable, and it gives you the correct necessary insights relating to how everything pretty much works, which is really cool. So I'd recommend you go look at that if you have any interest in gaining a better understanding around the general functionality within that code that we just basically explained. And also if you want to build on your own understanding or build on the general examples themselves. Alternatively, I would recommend to check out Security Tube, which is pretty cool, where you can find tons of stuff relating to this. So I think one thing that would be interesting to do is to generally go over code and define or explore what one's done in relating to that, just to sort of have a refresher, and also just improve a better understanding or perspective of how systems work, and general varying techniques relating to how to work with the various objects within a particular environment. So here what we have is we have a bunch of different techniques that are demonstrated in C. The project itself, it's a Visual Studio project, and don't really have much experience working with these particular types of IDEs, so the project itself is a bit messy in essence. But if we look in here, this was from the Security Tube training relating to Windows programming techniques, malware development techniques on Windows. And basically here what this does is it performs a special type of injection into another process, which is called an APC injection. And basically what we're doing here is we have a function to get the process, and what that does is it creates a handle, and then the handle is basically like a file descriptor in Linux, and then we have a structure for that file descriptor. And then what we can do is we can then take the size of itself in essence, and place that in there, as I think that's a relevant component to the actual overall structure. And then we have the thread 32 first section, where we use this to loop through the handles for a particular process or threads within a particular process. And then we perform a loop here that pushes this into a particular data structure, thread IDs. So if you use pushback, it pushes that onto the thread ID's data structure. And then here we have thread 32 next, which just basically moves to the next thread. So that's what's happening here. And then here we close that particular handle, and then we return the thread IDs. So with that understanding, we can see here that the thread IDs here are then opened, and then a context is set, and then we perform a mechanism such as get library on the particular thread itself, and then that then sends whatever the buffer is. So if you look here and we try to find out where that actual buffer is, okay, so we get the buffer from this particular location here, which is the virtual memory allocation. So here we actually appear to be injecting into the actual thread memory space itself, and then writing to that memory space, and then calling get proc address, which then loads the particular library which has been specified at the buffer location. So that's how that pretty much works in essence, and I think that is a method of actually, utilizing memory, assuming you have the correct permissions, to actually write in the necessary data is something that I feel like that's probably pretty key. So we create the memory here, the memory structure here, then we put that into the buffer, then here we write the memory space, and then here we write that memory, that virtually allocated memory, into the actual queue user space APC. Now here we have the buffer, and then here we just have the specification of the actual thread, and then that actually enables that DLL to be loaded within the memory space of a particular process, which is a pretty cool thing from my perspective of things. So the way that this particular functionality works in essence, this is hollowing, which is pretty interesting, where we actually take the process itself and then we perform the necessary modifications to it to ensure that we can actually place an alternative exe into that particular process space, and that has a number of different benefits within itself. So create a file to create file to local file that will be loaded into the runtime process. So what we want to do here is we want to just allocate space in the new process that is equal to the size of the replacement exe. So basically what we do is we load the file into memory with the necessary parameters. So we have the file handle there, and then what we do is from that file handle we do virtual allocation while getting the size, measurements and everything of that nature to ensure that that's accurate in one sense or another, so that we can have a new address space where we can place that actual file. And then once we have that, we can then do necessary calculations to ensure that the image sizes are modified, and then once they have been modified, we then perform the rebase image 64 replacement, which has the necessary components to ensure that the image is rewritten correctly, so that it accommodates the new size, including the newly allocated memory. And then here we close the file handle because it's no longer necessary, because we created a file mapping here, and then that file mapping is then mapped into the necessary address space. Here's a file. Then these are just necessary things for the function, and then once we have that, we just do alternative modifications and then write that process into memory. So here we created the map for it, and then here we write that process into memory, and surprise that, oh no, we'll do that there, and then here is just the, yeah, cool. So then that's, so here's just the structures. We use this address here, and then that should be okay. And then the main thing, and then some things relating to the actual data.sec section and a number of other things necessary to just ensure that, you know, the system image itself, it's still valid. And then I'm not too sure exactly as to, okay, so here we modify the entry point because I'm not sure how then you go to run the next piece of necessary code, but here we modify the entry point and set thread context, and then after that we resume the thread and close all the necessary handles that are no longer being utilized. So that's pretty much that for this, and that's how process hollowing works. I'm just not sure as to how you'd actually get that to be the runtime thing without within memory, because the process itself would have already started, unless if it's a process. So let's see. Okay, so I was thinking that whether or not that could actually be whether if we suspend the process or thread at runtime at the start, or if we spawn a thread from. Okay, cool. Now it's so good. So I think that either you create a new thread with the necessary entry points, because we modify the entry point, so the next thread might actually begin at the new image location, and that's in essence the concept of the process of actually hollowing the process itself, because once you've modified those key data structures, you can then utilize whatever necessary things are required in relation to actually getting the things or the code that you have to execute on the actual system itself. So I thought I'd do a quick one on thread hijacking as well. Thread hijacking is the process of actually taking over a process's execution flow as though through a buffer overflow or something of that nature. And in this particular process, what we're going to do, we're going to set, we have the main function here, and what we're going to do, we're going to open process into hprocess once we find out the necessary process and provide the DLL path. And then what we're going to use a function called getFirstThread, and basically what that does is it just basically creates a loop, as mentioned previously in the APC inject. It just loops through that to try find varying threads, and if it finds a thread that matches the PID of the process, then it actually, the PID which was provided here, then it would actually put that into the TID, and I believe that the TID struct or count, it's an int. I would have thought that it would have been an array, and there's no real specification of what we're actually looking for in this particular thread section itself. So there's no like particular permissions that might specify when it would actually break, but just I think when it matches the PID, then that's okay. Then what we do is we open thread. We open the thread with the necessary permissions, providing the TID here, and then we hthread, and then here we do, if a thread fails to open, error pretty much, and then we do inject. And basically what do inject does is it hijacks the thread, and it does this through a number of different things. It's a bit of an assembly here. It has an if statement based on the architecture of the system, how it will operate, and then what we do is we do virtual alloc.exe into the buffer to ensure that there's a necessary space there. And then we set some contexts that enable us to control specific flags. Then we get the address of load library. Then what we do here is basically amend varying things on the actual binary itself. You should be doing with an IDE be better. And then we modify things in this particular in this assembly language code here, which will enable us to basically run our DLL once we load the process. That's why we put this address of load library, and also the address of EIP, which I believe will point to that, or we will have some near reference to this. And then that's pretty much that. And then once that's done, we change the address of EIP here, or RIP here if it was a 64-bit architecture. Based on that, there's some if statements. and else's, and then here we do set thread context, which is basically set the context that we've provisioned here and a bunch of other places here, some of those flags there. And then resume the thread. So then when the thread resumes, it actually continues executing from the buffer that we've constructed here, and that we've allocated memory for here, and that we've set the necessary permissions for here. That's pretty much it, which is pretty interesting, and I think that's a really cool way of developing code and working through varying systems.